Greetings to all students. Now in this video, I'm going to explain about the mechanism of dehydration of alcohol, but with additional step which is rearrangement. Now in previous video, I show you the mechanism of alcohol. We have 3 steps. We have step 1, 2 and 3. But in this mechanism, I'm going to add one more step. And as I mentioned before, it's about rearrangement. So basically, why rearrangement? Because okay, now if you remember in the mechanism of dehydration of alcohol, carbocation is produced. Okay, it is produced as intermediate. Now perhaps you might get like primary or secondary carbocation. One of the characteristics of carbocation is that it likes to do rearrangement to get more stable carbocation. So most likely if you get primary carbocation, you can rearrange it to secondary or tertiary, or from secondary you can arrange it to tertiary, which is getting more stable carbocation. Now for this to happen, there are two types of rearrangement. The first one is what we call as hydride shift, and the second one is methyl shift. Now we call it 1,2 hydride shift, and the other one we call is 1,2 methyl shift. So I'm going to explain why it is 1,2 and why it is hydride and why it is methyl. So I will directly go to the first example. Okay, you can refer this at page 43. Now if you look here, we have the formation of product from this alcohol. We have three methyl. Okay, if we name this is 3-methyl to butanol. Okay, so from this 3-methyl to butanol, we react if with concentrated H2SO4 and we heat it, we are going to get product A and product B, and both products are alkene. But we have to identify which one is the major product. Okay, now let's see. Between A and B, can you decide which one is the major product? Yes, the answer would be A. Why? Because A has what we call as 1, 2, and 3 alkyl group attached to the carbon-carbon double bond. Whereas for B, we only have 1 alkyl group here, whereas the rest is H. And therefore, our major product will be A. Now, in these questions, okay, it asks us to write the mechanism for the formation of major product. So we only focus on the mechanism of major product. So let's proceed. Okay, this is page 44. Now, what will happen? So we have here okay, you better open the structure. Okay, this one. Now, in step 1, it will react still with H2SO4 that react as catalyst. Okay, so what will happen here? Now, let's focus on this bond. This bond will undergo heterolytic cleavage, where both of the electron will be given to oxygen. Okay, both of the electron will be given to oxygen, and we are going to get OSO3H minus. What will happen to the H? H lose its electron and H plus or hydrogen ion is produced. And since hydrogen ion is not a stable ion, it usually will attach with anything, and in this case, these two lone pair will be donated to H plus to produce this. So this is the electron just now. Okay, this is the electron just now, the lone pair. Okay, now let's take a look at this side. Now oxygen has 1, 2, 3, 4, and 5 electrons surround it. According to the formal charge, oxygen has 6 valence electrons, but because there are only 5 electrons assigned to the oxygen, therefore it is less 1 oxygen, and that is why oxygen become positive. Okay, so that's what we call protonation of alcohol. Protonations of alcohol. Okay, so our alcohol had been protonated. Now let's proceed with the second step, which is the formation of carbocation. So we have here, okay, we rewrite back. Okay, so in this step, like I mentioned before in the previous video, the formation of carbocation is also where H2O is removed. So I advise you to add this, the removal of H2O. So if you look at this structure, this part is the one that is look like H2O. However, H2O must have 2 lone pair. Okay, H2O must have 2 lone pair, so that usually we can get. So we can get it as H2O with 2 lone pair, and we have 1 lone pair here. So what will happen? Now this bond will undergo heterolytic cleavage. This is between C and O. O is more electronegative, and thus both of the electron will be given to oxygen. So when 2 electron is given to oxygen, that is where H2O is formed. And the rest we are going to get this. Ke3. There's no longer bond there. Now guys, boys and girls, we have here 1, 2, 3 electrons surround carbon. Carbon has 4 valence electrons, but in this case we only have 3 electrons surround it. This makes this carbon become positive. So this is what we call carbocation. Now can you classify this carbocation? You are correct. This is secondary carbocation. And I told you, whenever you get carbocation, stop for a while and see whether you can do rearrangement or not. In this case, yes. By how? Now let's see the step 3, which is rearrangement. Okay, in this case, okay, I better open this. Okay. So this is will undergoes 1,2 hydride shift. So what it is now? What will happen? Okay, these two, it seems like they are going to shift place to each other. Okay, so we name it 1,2, which because it's not representing carbon 1 or carbon 2, but more to like neighboring carbon, like this 1, 2. Okay, so what will happen? We are going to change place and we are going to get this. Here is the positive and here is the H. So hydride is referring to hydrogen. So they are likely to shift place. Now this is your secondary carbocation. Can you classify this carbocation? Yes, now the answer is tertiary carbocation. So please remember, whenever you bump into carbocation, stop for a while. Okay, you stop for a while and then you see. Okay, you see whether you can do any rearrangement or not. Okay, basically look at the primary and secondary carbocation and see whether they can be rearranged to produce more stable carbocation. Okay, so now we have tertiary carbocation. We go to the last part. Okay, here it is. So at this part also will come back. Here also will come back to produce back HOSO3H, which means they will take one H. So which H? Okay, they will take this H. Okay, they will take this H. Okay, I'm sorry, I think should draw it like this, from the O to the H, only H plus. Okay, only H plus. So there you go, you can get the HOSO3H. And it leaves these 2 electron here. Ada 2 elektron tertinggal di sini. So what will be happen? These 2 electron we give here. Okay. So if I can say, wait. If I can make, okay, say this is the green and say this is the yellow. So what will actually happen? The green goes here and the yellow can be placed here because this carbon, this next carbon only have 3 carbon. So if we give another one, there will be 4. Okay. But we don't draw it like this. We just let it like this and we get the double bond. And there you go. This is our alkene. Okay. Now, I will show you the second one, which is a rearrangement where methyl is involved. Okay, so let's just proceed to the next one, page 45. So I will directly give you the final answer. Yeah? So this one we're going to get this. Oh no, this is CH3. Okay, you're going to get this major product, or the other one is okay, so we have A and we have B. Of course, obviously, A is the major product. But as you can see, up here is supposed to be H, right? But we change it to CH3. So why these things happen? Now, let's see. Go to the first step 1 as usual, the protonations of alcohol. So still with sulfuric acid. So this bond undergoes heterolytic cleavage and it will produce OSO. Okay. So still, as usual, same thing goes where these two will attack H and this will be formed. You can pause this for a while, this video. You can do it first if you want to try to see whether you understand or not, and then you can play it again, yeah? So we have this and become this. So like I explained before, oxygen is surrounded with 1, 2, 3, 4, and 5 electrons, and this make it positive. So this is the protonations of alcohol. Now let's see. So we have here okay, this one, and then what will happen? Oh, sorry. Like I mentioned before, this is where removal of H2O happen. Okay, so this bond will undergo heterolytic cleavage to produce what we call as H2O. Okay, H2O. And at the same time, carbocation is produced. Yeah, this is produced. Right? And as you can see, this is our secondary carbocation. So again, stop for a while. See. Okay, my tips also, you can look at this carbon and at this carbon. Okay, you look at this carbon and also this carbon, and you see if you make a shift, okay, between the next carbon at the left side or at the right side, can they produce a stable carbocation or not? So let's see. I'm going to move it to the carbon at the left side, and if you look at the left side, which is if you look at this carbon, it only surrounded with methyl. Okay, so we can do methyl shift. Okay, we can do methyl shift where the positive will be here and we move the methyl. So as you can see here, we can produce tertiary carbocation. Okay, so we go to the last step. Go to the last step, which is this. Now we have our tertiary carbocation. We have H here, and we have CH3 here, and we have another CH3. Then the also is coming again. Oh, sorry. Not this one. We have this. Okay, if you don't add this plus also, no problem. So, it should take, okay, if you think, become this one, right? Okay, don't get confused. I know we usually look at this side, but don't forget we also have another H up here. Okay, so this will take the H here to produce the H2SO4 back, and this bond, okay, this bond will be given here to produce alkene. Okay, there you go. The mechanism of dehydration of alcohol with additional steps rearrangement.